Diamonds in Minecraft are both a status symbol and a useful item. Before netherite, they were the best for gear, weapons, and tools. They are commonly used as a form of currency, and just making piles of the blocks is a flex. This is largely because it has to be mined, or maybe you find a few in a chest. But there are no farms for it. In real life, diamonds are also status symbols, even if it's unwarranted. But we actually do have farms for them, and they are incredibly useful minerals. Coal in Minecraft is one of the early resources you seek out to start cooking and smelting, the beginning of progression to more advanced materials. In real life, it's been used by humans throughout history, but our thirst for it has skyrocketed since the Industrial Revolution. If you are new here, I'm Nice, and I'm a geologist. In this video, we will talk both about diamonds and coal. Where do we find them in Minecraft, as well as in real life? How do they form? When did they form? And what are their properties? I'm going to cover both, not because they are related to each other in the game or in real life, but because they are related in people's minds. There is this misconception in real life that you can just squeeze coal enough and it becomes diamonds. In Minecraft, they are almost exclusive to each other when you go mining. As you dig down, coal stops and diamonds start. Maybe this is trying to say that the carbon that makes up the coal is the same that makes up the diamonds. They are both composed of carbon, but they have two very different origins. We will start off with ore distribution in Minecraft, and like the iron ore episode, we will use this mountain. First, let's clean off the organics and sediment, and then we can bring it over for a closer look. It's 256 blocks on a side, and it gets cut off at the max world generation height. I have edited the world gen to remove caves, veins, structures, anything that inhibits ore from generating. Lastly, we can add a graph on the back for elevation. We can remove everything but the coal and diamonds and see the general distribution. This is still a bit cluttered, so we will look at each batch of generation individually. During world gen, coal generates in two groups. First, it tries up high between Y136 and 320, even though the top is higher than normal world gen. This is just a flat rate with the abundance being the same at every elevation. It then tries between 0 and 192, with more abundance in the middle at 96. The second batch is also less likely to spawn if it would be exposed to air. Diamond generation has 4 separate spawning behaviors, and I think it's just overly complex. The first 3 are all between Y16 and -64, with increasing abundances as you go deeper. The wiki states Y equals 14, but I think that's wrong. The code specifically says 80 above the bottom to -80 above the bottom in a trapezoid shape, which is 16 to -144, with the most being at -64. If I'm wrong, I'd like to know what I'm missing. And just looking at the immediate region, here are 3 that are at 15. It might be rare, but I have some data for 16 as well. 3 sizes of ore try to spawn in this range, and all of these values will be per chunk. Small ore blobs try to spawn 7 times, with a 50% chance to not spawn if exposed to air. Medium ore blobs try to spawn 4 times and do not generate if exposed to air. And then large ore blobs try in 1 out of 9 chunks, with a 70% chance not to spawn if exposed to air. A 4th type tries to spawn medium ore blobs 4 times between -4 and -64, with the same abundance at every level. And it has a 50% chance not to spawn if exposed to air. Mojang reduces the amount of ore that is exposed to air to prevent players from just running through the caves to find exposed diamonds, and reward players for actually mining. There was no air in my mountain, so everything generated. We will talk more about air in a second though. We can reload all of the ore and then squish it into a graph to look at its abundance per layer. In general, coal is most abundant at Y136. This is different from what you see on the wiki. It shows peak abundance at Y45, and this discrepancy is due to air. Some comments on the iron ore video said leaving caves in would be more accurate, and that depends on what you're talking about. If I left caves in, it would be more accurate for this specific area, but even this 256 by 256 area, it's not big enough to average out the noise that would be added from caves. My goal here is to look at overall distribution, and I think not having caves there is a little bit more accurate to give you the general idea. But we can do better. On the opposite end, the wiki chart is averaging over a huge area, most of which is not mountainous. And most players aren't mining like huge areas. A viewer of the iron ore video gave me data they collected on every block in a 50k by 50k area. Let's plot the coal and diamond abundance from that. We have more data, so the randomness gets smoothed out, but the upper coal almost completely disappears. And this is basically the graph you see on the wiki. If you were going to mine everything in a huge area, or had no mountains around you, then I guess Y45 is where it's at. But in reality, you aren't going to try to mine air. You'll ignore it. So here is Soggy's data if you ignore water and air. If you are just mining like a normal person, then head to a mountain, mine at Y136, and that is where you will find the most coal. Diamonds, on the other hand, don't really change much either way. They're basically just a triangle with increasing amounts as you go down. This is why I think current gen is just overly complex. Just make it more abundant as you go down and one value for air exposure. Maybe they can't vary the size of the ore blobs like they want with one generation or something. If I'm missing something here, I'd also like to know that. And thank you again to Soggy Cat for the data. I will be using it in the rest of the ore episodes as well. Oh, and before you type that comment, yes, both diamonds and coal can spawn as part of fossils too. We will talk about this in another part of the video. Let's look at the in-game amounts from our excavation so we have something to compare to real life. There were nearly 7,000 blocks of diamond ore in the mountain, which with Fortune 3 would yield about 1,700 blocks of diamond. Coal, on the other hand, was nearly 20 times that, 140,000 blocks of ore to produce 34,000 coal blocks. Let's compare these values to real life for what we mined globally last year. I will list my sources for all the data down in the description if you would like to read more. I don't have values for how many gem quality diamonds were mined last year, but we did mine 41 million carats of the useful version industrial diamonds, which isn't really that much since 1 carat is only 0.2 grams, so that's only about 2.34 blocks. Nowadays, we grow a lot more diamonds than we mine. Last year, we grew about 15.5 billion carats, which is still less than we got from the mountain. We will talk more about diamonds later, but let's talk about real-life coal first. Coal comes in a few varieties, or grades, which go up in density and carbon purity. There is also peat, which can be considered a precursor to coal. It's mostly just unaltered plant material. This can convert into lignite, the lowest grade of coal, and then bituminous, and there's also sub-bituminous between these two, but I don't have a sample of that, and I guess geologists just weren't feeling creative enough to give it a different name. Above that is anthracite, the highest grade. It has this great sheen to it. I have this big chunk as well, which will get used later in the episode. Globally, these types of coal have different abundances, with both types of bituminous coal comprising the majority of what we mine. For the Brits, I'm talking about bituminous coal. Last year, we excavated more coal than ever in history, nearly 8.7 billion metric tons. If we use the coal abundances, we can calculate the average density and then calculate a total volume, which is about 6.5 billion cubic meters, or a cube that is about 1,873 meters on a side, just from last year. Here they are at 1 to 2048 scale. We are here, and here's also the iron cube from last episode. And I was curious how much total coal ever was formed on Earth. I found values for total energy produced from coal since 1900, and we know how much energy comes from coal, so we can back calculate a decent estimate of total volume. We have estimates for total remaining coal reserves, and if we sum up what's left with what we've used, we get a little over 1 trillion cubic meters, or about 10,000 blocks on a side. This is what that would look like at the same reduced scale as our map versions here. Coal is not a mineral like many other Minecraft ores. In real life, it's considered a sedimentary rock, meaning that it's made up of particles of sediment. Most sedimentary rocks are composed of minerals or small rocks, but coal has a large amount of organic material, greater than 50% by definition. If it's less than 50%, then it might be considered something like a carbonaceous shale or mudstone. Minecraft coal has these little chunks in stone or deep slate, but usually in real life it's found as layers or seams. So let's go look at some real life examples. This is an outcrop of the Carbondale Formation in northern Illinois. Here it's mostly shale and sandstone, but at the base of the sandstone you can find some thin, discontinuous layers of coal. This one is very thin, and it could just literally be a single tree that is compressed here. On the underside of the sandstone, you can see some impressions of bark from some very old trees. Here is a low-grade coal horizon in Montana that is about a meter thick, and it's not very pure either, but you can follow this layer for miles. Going back to the definition of ore, it needs to be economically viable to be worth all the trouble of collecting it. Commercial coal mines and pits are usually much higher grade and or much thicker. Some of the equipment used in coal mining are the largest machines ever built. This one is nearly 100 meters tall. One of the more interesting things about coal is that 90% of it was made within only 60 million years, which sounds like a long time, but that's only 1.3% of Earth's total history. So to talk more about that, let's go over to the geologic timeline world. This is still a work in progress, but this is a world that myself, some of my Discord, and members of the Prehistoric Fauna Mod have been contributing to and building. It is a representation of Earth's history where one block going down this path equals 1 million years. There's a diorama with a bunch of custom resources that are being built, and I'll be making it available for download once it's done. But for now, let's go 300 million years into the past. Nearly all of Earth's coal was produced during the aptly named Carboniferous period. This is the time that is famous for giant insects like Arthropleura and Meganeura, and one of my favorite weirdos, the state fossil of Illinois, the Tully monster. If we look back into the Silurian, about 60 million years before this, the first vascular plants had evolved, and they were just these short little things, like Cooksonia. But they had special tissue to transport water and nutrients. This allowed plants to start growing up and away from water. By the end of the next age, the Devonian, plants had evolved lignin, one of the main components of wood, alongside cellulose. This allowed them to gain great heights. Wood has evolved several times independently in history, and the term tree really is just a word for a plant that has a stem or a trunk. Modern trees didn't necessarily evolve from prehistoric trees. Acacia trees are actually legumes and more closely related to green beans than they are to an oak tree. And an oak tree is closer related to a tulip than it is to a pine tree. In the Devonian, Archaeopteris was one of the first trees and regularly grew over 24 meters tall. By the beginning of the Carboniferous, other species like lycopods, tree ferns, calamites, seed ferns, chordates also had wood or other compounds and structures that allowed them to grow tall and compete for the sun and get those tasty leaves away from predators. And these are the main species that contributed organic material to what eventually became coal produced during this time period. A popular theory for why so much coal was produced is called the evolutionary lag theory. The thought is that lignin had evolved, but nothing had evolved to break it down. So trees would die, fall, and just lie there. They would pile up, get buried as big pieces of sediment, and got converted to coal. Eventually, fungus and bacteria evolved to take advantage of all this great energy just lying around, and less material made it to burial, so less coal was formed. The idea of these old trees just laying around for millions of years is pretty fun to think about. But there are a few things that put holes in this theory. When analyzing coals from this time period, many are composed of lycopod material. These were the fossil trees that were in that sandstone overhang. Here is a closer look at the texture of the lower bark. They are commonly called scale trees, and Lepidodendron is a common genus. The thing is, they don't have much lignin, and there's actually no correlation between coals high in lignin and times when larger volumes of coals were produced. A different explanation is a combination of two things. To produce sedimentary rocks, you need a low point for the sediment to settle in, and you need a source of sediment higher up. Weathering will break things down, and gravity will eventually carry things to a low point. Everywhere on Earth can be classified as a sediment source or a sediment sink. Globally, the ocean is the ultimate sink, but locally, it can be a little puddle or anything in between. A major geologic event that was going on during the Carboniferous is the formation of the supercontinent Pangaea. Here is a simplified cross-section of the continents of Euramerica and Gondwana. The continental crust is thick and the oceanic crust is thin and more dense. All of this is floating on the mantle. The denser oceanic crust was subducted under the Gondwana continental crust, and eventually the continents collided. These collisions thickened the continental crust, and this process was responsible for 2 of the 4 events that built the Appalachian Mountains. So this creates our high point for the sediment source, but that's not all. This increased mass sitting on the mantle actually causes the continents to sink. This was happening at the same time, but I'm just showing this as two separate events. This pulls the areas near the mountain down as well and creates a basin to catch sediment. The second part is the organic matter. A large part of Pangaea was sitting on the equator, and like today, that's a great place for plant production. River deltas were dumping sediment into these basins, and they were swampy as well. The waters would have had low oxygen, which further decreases the ability to decay and rot. This perfect storm came together to bury massive amounts of organic material, and by the end of the Carboniferous, Pangaea was fully formed, the basins were filled, and coal production on this scale has never been seen again. Now that we have a bunch of organic material buried, let's talk about how it becomes coal. It goes through a process called coalification. Creative, right? The process of converting plants to coal is more than just compression. The water and pore space is quickly squeezed out, and even though the material is then dry, there are still volatile compounds present. Here is the structure of lignin, and here is cellulose, or part of one. It forms these long chains. This is what cotton is made of, by the way. We only need a few of them. They have a lot of these carbon rings. If you aren't familiar with organic chemistry, there is a carbon atom at each one of these unlabeled bonds. They both have these volatile components as part of their structure as well. If you increase temperature, these volatile components break free and the remaining carbon can convert into something that looks like this. Many more complete carbon rings and not many volatiles. This is a simplified model of what a coal molecule would look like. This is a similar process to how oil and gas is produced, and most natural gas is produced from Carboniferous age sediments as well. Most oil is younger. This is also how charcoal is made as well. We burn coal to raise the temperature and drive off the volatiles. We just make sure that the oxygen level is low enough that it doesn't burn everything up. So what about Minecraft fossils? Coal ore can replace part of the bones in fossil structures, but real bone is mostly made of the mineral apatite. This does not have volatiles that detach when it's heated. It can metamorphose into other minerals, but it won't change into coal. So coal replacing bone isn't really based on anything that happens in real life. Love that sound. And one more thing before we go back to the other world and talk about diamonds. Let's address clean coal and climate change a bit. Like we talked about earlier, coal is a sedimentary product, so there are usually other bits and pieces buried at the same time. But the term clean coal isn't really used to describe the purity of the coal itself. Clean coal usually means mitigating the harmful products produced when it's burnt. This example here has some sulfur and nitrogen in it, and when it burns, they produce sulfur dioxide and nitrogen oxides, which then creates acid rain in the atmosphere. It was a big deal in the 1980s, but we added engineering solutions to remove these products, and the amount of acid rain decreased. But even in ideal conditions, the biggest issue is the production of CO2. Over the 60 million years that all of these plants were taking CO2 out of the atmosphere and getting buried to make this coal, the planet went through some huge changes in temperature. Here is a display of global average temperature during the time. The orange is hothouse conditions, and the blue is ice age. Near the end of the Devonian, when we started to get real forest, trees were taking up CO2 and putting out oxygen. Global temperature dropped, and we entered an ice age. The planet remained in one for the entire Carboniferous, and it nearly went into snowball Earth territories several times. Global climate is very complex, and these changes took place over millions of years. So other climate systems had time to adjust and tried to stabilize. In the last 125 years, or nearly instantaneously at this scale, we have put 25% of the CO2 that was taken out over those 60 million years back into the atmosphere. At our current rate, we will use the remaining 75% of coal left within the next 125 years. I don't want to be a downer, but we are in for some wild changes. Let's head back and talk about some pretty rocks. Okay, I'm going to take this graph with us, and we're going to go back to the normal dimension. And I'll put the graph over here. A common misconception is that diamonds come from coal. Coal is a rock, but diamonds are a mineral composed of pure carbon. Earlier we talked about pressure, but mostly temperature making coal. The effects of the sun, weather, and season really only reach a depth of roughly 10 to 20 meters. Below that, the temperature is dependent on the heat from the core and the mantle. In the upper part of the continental crust, Temperature rises about 25 to 30 degrees C for every kilometer you go down. This is what cooks the coal. Even though anthracite forms at 7 kilometers deep, it's still an incredibly shallow process geologically. We can plot these temperatures and pressures on a graph to compare. We can first add the trend of temperature for the continental crust, and then we can add the positions of the coals. Besides diamond, there is another mineral that is pure carbon. At around 9 kilometers down, carbon can convert to amorphous graphite. It's light, shiny, has a really high combustion temperature. It's the same material we use in pencils. Graphite and diamonds are allotropes, meaning that they are composed of the same elements, but have a different molecular structure. And before we go deeper, let's talk about deep slate. Slate is a real metamorphic rock. It starts as a mudstone, and with pressure and temperature, it undergoes metamorphosis. We'll talk more about metamorphosis in the lapis episode. But in real life, this happens around 5 kilometers down. So if the deep slate in Minecraft is at Y0 or about 0.1 kilometers deep, there are two options. It formed deeper and then was uplifted, which doesn't make sense given that it's the same horizon everywhere in the world, or the pressure and temperature with depths is not the same as on Earth. I don't want to lorecraft here much, but people often say that the gravity in the Minecraft world is greater than Earth's. I assume because the size of the Minecraft world. I haven't looked into that, but if it was true, then you could get higher pressure and temperatures at shallower depths. But diamonds still break this idea though. Slate is considered a low-grade metamorphic rock. If you keep adding pressure and temperature, it changes to phyllite, then schist, and then gneiss. After that, you get partial melting, and the rock is called migmatite. And beyond that is full melting, and then it's just magma. Let's try and figure out a squished scale for a Minecraft world. Let's change our chart here to metamorphic rocks, and add the values for surface and slate formation in real life and Minecraft. Based on that, we can do some math for the rest, and figure out that gneiss would be forming at around y equals negative 230. But real-life diamonds don't start forming until greater than 150 kilometers deep. So even at a compressed Minecraft scale, diamonds would not start to form until deeper than negative 1800. So in my opinion, diamonds cannot be forming in deep slate any way you look at it. Which is interesting because in real life, most diamonds don't form in the rocks we find them in either. Let's talk about where diamonds come from. On Earth, it's very uncommon for surface carbon to be buried to the depths needed to make diamonds, and then make its way back to the surface. There are some diamonds called carbonados, which might actually be just that. So I will concede that it's not entirely false to say that some diamonds could be made from coal. It's just incredibly uncommon. A second uncommon method of diamond production is impacts. When a meteorite impacts Earth, it can create the high pressure and temperatures needed to form diamonds. Those conditions don't last long, so these diamonds are usually very small. Where most diamonds come from is a rare form of volcanism. The two most common types of volcanism people think of are either hotspot volcanoes, like Kilauea on Hawaii, which is on top of a mantle plume, or stratovolcanoes, like Mount Hood in Washington State, which is part of the Ring of Fire. And the volcanoes and earthquakes associated with that are the result of subducting slabs. Diamonds, however, come from a strange, small type of volcano, and there happens to be one in Upper Peninsula, Michigan. Let's go check it out. Since the late 1800s, some diamonds have been found in glacial sediments in southern and central Wisconsin, but we didn't know where they were coming from. And at the time, it was a relatively new discovery where any diamond was coming from. Previously, we only found them in sediment, being weathered out from some other original mystery rock. During some logging in the 1970s, a strange-looking rock was uncovered near Lake Ellen in the Upper Peninsula. And here it is. This unassuming pit is what's left of a volcano. The rock is called a kimberlite. Looking at a hand sample, you can make out a variety of larger minerals. It breaks apart rather easily, and it's a pale greenish blue. The structure of what's left of this volcano is called a kimberlite pipe. From mining and exploring other ones, we have learned that they kind of have a carrot shape. They are usually small. This one runs out into the woods and is about 150 meters across. Kimberlites are very strange, and they are a geologic topic that we still have a lot to learn about. And like I said earlier, diamonds weren't even a part of this rock or magma originally. Let's look at geologic time. This is the map from the geologic timeline world. The formation of Earth is here. Large multicellular life is here. Dinosaurs died here. And then we're at the end. These kimberlites are normally found in Archean-aged rocks. Technically cratons. Cratons are the stable cores of continents, usually billions of years old. Most diamonds are older than 500 million years old, which makes sense if they are commonly found in these Archean-aged rocks. You can't put one thing inside something else if it doesn't exist yet. So the rock had to exist for a volcano to go through it. The weird part is that kimberlites are mostly a geologically recent event, most of them being younger than 500 million years. So these young volcanoes only erupt into these incredibly old rocks. But where do diamonds fit into this? The diamonds form in an area called the Diamond Stability Field. This is greater than 150 kilometers down, but the kimberlite magmas that bring up the diamonds form even deeper. It's not really actually known for sure how deep, but likely more than 200 kilometers. Most magmas can take years to reach the surface, but kimberlite is fast, estimated at only taking days or hours to reach the surface. The magma itself is strange. Besides only forming under old parts of the continents, it produces only a small volume of magma, and it's incredibly high in volatiles like CO2, which likely helps it rise so fast. As the kimberlite is coming up, it can grab onto pieces of material that it's going through. This doesn't just include large chunks like in my diagram, but lots of other bits from the walls, including diamonds. These foreign bodies are called xenocrystal if they are minerals, or xenolith if they are rocks. The Lake Ellen kimberlite pit has a xenolith. This rock here is a older rock that's embedded inside the younger kimberlite. So it came off of a wall as the magma was coming up, and then when the magma cooled down, it was kind of left floating in there. When the magma is rising, it can pass through a zone of diamonds, and they get picked up to come along for the ride. Diamonds being minerals are xenocrysts, or foreign crystals. Other magmas that form deep in the earth might pass through this diamond field, but they take too long to get to the surface. Once the diamonds are out of their stability field of pressure and temperature, they can be oxidized or reabsorbed into the magma. Not really melted, but altered into another mineral. And technically diamonds are metastable at the surface. The most stable state they could be in is graphite, but they lack the energy to break the bonds. And not all kimberlites have diamonds. There are about 3,500 identified kimberlites in the world, but only about 100 diamond mines. And sizable diamonds have never been found at Lake Ellen. So it's probably not the source of those diamonds that were found in the 1800s. And the real source is still unknown. And it's not as easy as looking for that classic volcano shape. The Lake Ellen kimberlite is about 180 million years old, and even though I called kimberlites geologically young, they are still old for topography. The Appalachian Mountains are considered old, and they were huge when they formed, but 300 million years can really wear you down. For Lake Ellen, the glaciers took care of everything that might have been sticking up. Let's move on and talk about diamonds themselves. Personally, I don't think diamonds are that pretty. I'm not a fan of cut gems in most cases. Give me a naturally formed garnet or a cube of pyrite any day. Diamonds also have a lot of issues behind how they are mined, and the prices are artificially inflated. Synthetic diamonds are now more pure and optically clear than real diamonds, so sellers try to tell you how it's the impurities that make natural diamonds special. It's all just marketing. They are very useful though. It's common knowledge that diamonds are the hardest mineral. I have an engraver with a diamond tip at work, and we use them in all sorts of cutting tools. This is a diamond wafer saw, and it has diamonds embedded into the blade. The geologists commonly use the Mohs hardness scale when talking about how hard a mineral is. It starts with talc, the mineral that makes up soapstone. My dad was a sheet metal worker, and he always had a piece of soapstone with him so we could write on metal, which makes sense, given it's one of the softest rocks. Next is gypsum, then calcite, then fluorite, apatite, orthoclase feldspar, quartz, topaz, and then corundum, the same mineral that make up ruby and sapphire. And then lastly, diamonds. I bought 100 carats of lab-grown synthetic diamonds for $100. They'll show up several more times in this video. These were meant to be used as grinding media, and they were the largest, cheapest synthetic diamonds I could find. The idea is that this goes from 1 to 10, and it's used for identification of minerals. You can pick a mineral, and then this mineral will scratch any mineral to the left of it. So
Fluorite will scratch calcite, calcite will scratch gypsum, topaz will scratch all of these, but it can't scratch corundum or diamonds.
But diamonds being a 10 is a bit arbitrary, because this is a qualitative scale, not a quantitative scale. If we compare some quantitative values for hardness for these same minerals, diamonds are nearly 4 times as hard as corundum. And there are only a few other rare minerals that even get close to diamond, and nothing really beats it. If we look at a single carbon atom, it has these 4 electrons in its outer shell. If we first look at the atomic structure of graphite, it's made of these sheets of carbon rings, and each atom is covalently bonded to 3 other atoms, which leaves one of the 4 electrons available to wander. If we convert these atoms to the structure of diamond, you can see that each atom is bonded to 4 other carbon atoms. This is an incredibly strong lattice, and this arrangement uses every electron in the outer shell. And we can actually see this electrically.
This is a multimeter reading resistance. If I take the 2 leads and touch them together, you can see that resistance goes down. Here's that piece of graphite from earlier. If I put the leads on it, it's also conductive because of that 1 free electron.
I also have a small probe that I can use under a microscope. If I touch the leads together, I get a value. If I grab the diamond with them, however, there is no flow of electricity because all of the electrons are bonded to other atoms. However, hardness is not toughness. Here are some diamonds on a block of aluminum, a soft metal, aluminium for you Brits. A diamond's hardness is its resistance to deformation. We use this property in geology for some experiments using equipment called diamond anvil cells, and we literally squeeze a small sample between 2 diamonds. Using this equipment, we can create hundreds of gigapascals of pressure for simulating conditions found deep in Earth. There are many more things that I could go into about diamonds, but this episode is already quite long. So now that we've discussed some things about diamonds and coal in real life, let's go over how I would adjust things in Minecraft. The diamond item was originally called emerald. It basically looked the same. It was still this blue color, which is fascinating because aquamarine is the same mineral, beryl, and it's a blue color. And there are blue diamonds, the Hope diamond being one of the more famous ones. The color comes from trace amounts of boron in the crystal structure. As for the shape, I don't know much about gems, but this might be a pear cut with a dull end or something. For the ore blocks themselves, you might find diamonds in slate. The diamonds came up in a kimberlite, they eroded out, became sediment, and then were redeposited with some mudstone, which then gets lithified, subducted, metamorphosed into slate, and then brought back to the surface. Probably not likely unless the diamonds are the same size as the mud, but it's possible. I don't know what's going on with the actual texture. Back when diamonds were added to the game, all the ore blocks had the same texture, just with different colors. They were slightly layered or maybe in veins, which really doesn't work for diamonds. They are normally found as single crystals floating in the kimberlite. The texture is so iconic that when they updated all of the other ore, they kept diamond the way it was. And I'm not going to try. I'm fine with the way it is. But I will change the host rock. Here's my version of kimberlite and the diamond ore version. Mojang has to balance a lot of things. I don't think Minecraft is a game for kids, but a lot of kids do play it. It's important to have some things accessible to everyone. Geologically, I'm not a fan of all the ore being everywhere, just at different layers, but as a game, it's understandable. Instead, I like how iron and copper have their own structures and places to go if you just want to focus on them. And I think that the other ores should have that as well. It's a lot more interesting than just going down and strip mining a whole layer. Diamonds should have kimberlite pipes. Maybe rarely found in a specific biome, but we really don't have rocks that you would find in an Archean age craton. Something like gneiss. But the pipe would be a funnel type structure that would go down to bedrock, and they would have a few diamonds in them. My example probably has too many. You would find the kimberlite exposed on the surface, and then you'd have to dig it out. Let's go talk about coal changes. For the coal ore, the classic texture is actually closer to how you would find small coal seams. And I'm not a fan of the newer style with these bigger chunks. 2 pixels tall is okay, but 3? You've gone too far. On top of that, we don't really know what stone is. If it's an igneous rock, like many people say, then it would definitely not have coal in it. If it's a sedimentary rock, then to have coal in it, it would have to be something like fine-grained shale or fine-grained sandstone. My opinion on stone is that it's something closer to limestone or dolostone, but you wouldn't have coal in that either. Actually, having it in deep slate is not that bad, but personally, I think the best way you could represent coal is just a solid block. Besides being found in layers, real-life coal is usually associated with specific sequences of rocks called cyclothems. If you look at a cross-section of some shoreline, you have the slope and sea level is at a certain elevation. Don't really think too much about the scale here. This is deep ocean, and this is the shore. Sediment is washing from the land into the ocean. Fine-grained particles can stay suspended in water longer, so you get clays out where it's deeper. Closer to the shore, you can have some marine organisms making calcium carbonate and depositing it, something like a reef. Closer than that, you have some tidal action and some beaches, and you have sand. Up on and near the shore, you can have some deltaic and swampy depositional areas. If everything just stayed the same, then sediment would advance and fill the basin. But what's really happening is usually a race between weathering, deposition, and the rate of sea level change, which determines a sequence of sediment that is deposited. It's beyond the scope of this video, but in geology, the field of sequence stratigraphy deals with this and trying to unravel old layers of sediment to determine what was happening at the time. This is why the Badlands look the way they do. They are a sequence of sediment laid down, and small changes are reflected in their color. Over time, these sediments will lithify, the organics can become coal, the sand becomes sandstone, the mud becomes slate, and if you just looked at a slice, you would have these layers. And this is what you normally see in outcrop. Here's a road cut from Pennsylvania that shows this in real life. So maybe coal in the game could be found as some layers, maybe replacing a small section of the Badlands in some variety of colors. I'm not really happy with what I have behind me, but hopefully you get the idea. Let's head back. And now that we've talked about everything in-game and in real life, it's time for me to make some blocks in real life. My goal here is to make a representation of their blocks from real-life materials, not recreate their look. The coal ore block presents a bit of a problem since there isn't coal ore in real life. I've decided to use this sandstone, which has these organic layers in it, and I'm hoping they'll be present inside when I cut it, and those will represent the little layers of coal. For the coal block, I have this beautiful block of anthracite, and it's almost a shame to cut it. I did buy it specifically for this though. It has these fractures in a few places, so I'll need to be careful with this one as well. For the diamond ore, I'll be using a piece of Lake Ellen Kimberlite. It should be large enough to get a 2-inch cube like the other rocks. It's also falling apart. Kimberlites, because they have so many volatiles in them, they easily weather once they're on the surface. My biggest problem is the block of diamond. Making a 2-inch cube of diamond is pretty much impossible. The largest synthetic diamonds are a little over 100 carats, and I would need one about 600 carats, and it also needs to be a cube. I have decided that the best way I can do this is to combine many diamonds into a cube with epoxy. Like I said earlier, I purchased 100 carats of diamonds, but that's only 20 grams, so I'm still about 500 carats short of making a 2-inch cube. But I can make a 2-centimeter cube. I also bought some blue dye for the epoxy because why not? It's probably going to look horrible with the yellow diamonds though. If you would like to help me achieve the dream of a 2-inch diamond cube, consider my Patreon. Besides letting me buy dumb things for videos, patrons get access to some exclusive content. Over on the Discord, there's a patron channel where I post drafts of animations and things I'm working on. If you're curious about my process, I've recently posted an early walkthrough of this world and script. I've also been going through my rock collections and talking about them and thinning out the herd. Some of these rocks ended up in the nice boxes, which this will be the last time talking about that. I made some loot boxes for April Fools, and there are only 20 left. Each one has a wood coaster that I made, a shirt that won't be anywhere else, a rock from my collection, or something that I used in a video, some stickers, a handwritten note, and I'm donating all the proceeds to the Nature Conservancy. If they don't sell, I'm taking them out of the store in a few days. Huge thank you to everyone that has purchased one. And if you do buy one now, make sure to tell me your shirt size. Also, thank you to everyone for letting me know that my stuff is being reposted on TikTok. Sadly, TikTok doesn't care. It's rather disheartening because these videos are the results of a lot of time and effort after my normal workday is done. I have spent months of time on this video, and it really sucks that somebody will just repost parts of it without even giving me credit. To the channel that's doing it, it's flattering that you think my videos are good enough to steal, but I ask you to be a better person. Let's see how the cubes turned out.
The cold cube turned out alright. The rock ended up staying together at least. It is a very pretty piece of sandstone, but I was hoping to have a couple thicker layers of organic material in there. But like I said, coal ore really doesn't exist. It's just coal. So if I did find a rock with like a thin layer of coal in it, it would likely be impossible for me to cut into a cube. Not bad though. The coal cube turned out really well. There's a few spots where it fractured, which I'm fine with. And there's a spot where it got stuck on the saw, so there's a saw blade mark here. I thought about polishing that out, but with all of the fractures, I don't want to push my luck. I'm afraid that it's actually going to fall apart if I do much more with it. I might actually use some epoxy to like stick it together, kind of glue, and make sure it doesn't fall apart anymore. The diamond ore block looks awesome. It has all these other bits and pieces in it. You can see all the xenocryst and xenoliths that are not part of the kimberlite that are all held together by the kimberlite. I kind of want to like actually analyze all these little spots and see what minerals they are. That'll have to be a different time. And for my tiny diamond cube, the top doesn't look that bad. I don't know how blue it looks in the video. Let's see if I can actually... It doesn't seem to be stuck to the walls, which is also a good sign. It's coming out. Well, it did settle out a little bit. You can see the top is more blue. But, yeah, well, there it is. I'm not really happy with it, but it looks cool. You can't even tell it's diamonds. It could just be glitter in there. Maybe I can try to find some synthetic diamonds that are not as yellow. The yellow color comes from nitrogen impurities, just from how it's made. All right, and I can add it to my other collections from the iron ore. Sounds great. I look forward to making versions of these for all of the rest of the blocks as well.
Okay, let's reset the mountain. Thank you to everyone that helped out in this episode. This one took me quite a long time to put together, and I hope you enjoyed it. I'll be working in Australia for a while, and I plan to start work on the next ore video, gold and copper, when I get back. There will be some smaller things out before that's done, I'm sure as well. I hope you have a nice day, and I'll see you next time. Goodbye. That's really funny. I make an entire world about diamonds and I didn't actually hold one. And then on top of that, there was a fourth type that Nice has commented out of the code. If you're new here, I'm a geologist and I'm nice. If you're new here, I can do this line.